telling you.
You look like you're fully what am I gonna do?
Okay, kiddos.
Google me right now.
Okay, we are continuing our zeros of polynomials lesson. We have 2 parts left.
Why are you coughing?
Okay, is it okay if I teach with my mask off? I'm gonna try and stay this far away from all of you.
No,
But
absolutely.
I will put it on.
Absolutely. We're the problems to you, so.
Okay, if anybody at any point gets uncomfortable, I'll put it back on. That's not a big deal. I just think you can hear me better. Okay, so we did graphing based off of the zeros that we were given in the multiplicity of those zeros. And then at the very end, we actually did one where we found the zeros by factoring, correct?
Yes.
So what we're doing today is we are learning ways to make finding the zeros a little bit easier. Because for the most part, when you can't factor as beautifully as we did in that last example, you start with a list of numbers and you have to work your way down until you find one or ones that work. So there are a couple ways to make this a little bit easier. The first way is called Descartes' rule of signs. Descartes' rule of signs allows us to identify how many positive roots, how many negative roots, and how many complex roots a polynomial could have. So if we do Descartes' rule of signs and we identify that there are no positive roots for this polynomial, I can take out all the possible positive values that I would have had to test otherwise. So this allows us to narrow our field a little bit. There are 3 parts to Descartes' rule of signs. The first part says that the number of positive roots that a polynomial will have is equal to or less than the number of sign changes in our original polynomial f of x. So by sign changes, I mean it goes from a positive term to a negative term or a negative term to a positive term. And these are positive real roots, okay, not complex. The number of negative roots for a polynomial is equal to or less than the number of sign changes when we plug in negative x. So the number of positive roots is equal to or less than the number of sign changes we have in the original function. To determine the number of negative roots, we have to plug in negative x everywhere there's an x, and we have to simplify. Then we count the number of sign changes again. The number of negative roots I have is equal to or less than that number of sign changes. The third part of this then says if the number of roots is less than the number of sign changes, it differs by a multiple of 2. So if I have 4 sign changes in the original f of x, I could have 4 positive roots, or I could have 2 positive roots, or I could have 0 positive roots. So the number of sign changes I get, I just keep subtracting 2 from that until I get to 0, or the last positive that I could have, which would be 1. Okay, you can never have a negative number of roots. So of course, we're going to do an example.
You mean 15 examples?
One example. And then we have just one more theorem left. Super duper fun. Okay. So the example I would like to do. I would like to find the number of positive, negative, and complex roots in the polynomial f of x equals 2x to the 5th minus 7x to the 4th plus 3x squared plus 6x minus 5.
It's supposed to be a complex root.
We're going to get there. I'll show you. Since we haven't really learned the trick for the number of complex roots yet, of course, we're going to focus on the positives and the negatives first. I always like to do the positive because it starts with my polynomial in its original form. So I'm going to write out what my polynomial is, and I'm going to count the number of sign changes that I had occur. So in its original form, I need to count the number of times it went from a positive to a negative or a negative to a positive. So I had a sign change occur between my first 2 terms, because my first term is positive and my second term is negative. I had another sign change occur between my second and my third, because it went from a negative to a positive. I did not have a sign change occur between my third and my fourth because they're both positive, but I had one occur between my fourth and my fifth because it went from positive to negative. So how many sign changes did I have occur? 3. So when I'm talking about the number of positive roots, I could have 3, or I could have 3 minus 2, which is 1. Remember, we have to decrease by 2 as many times as is possible.
Wait, what? I'm so confused.
Okay, so I counted the number of sign changes, correct?
Yeah. So
And I got 3.
Uh-huh.
But it doesn't say I have positive roots equal to the number of sign changes. It could be equal or less than. So if it's less than, it differs by 2. So I took 3, I subtracted 2 to get 1. So I could have 3 positive roots, or I could have 1 positive
What
root.
does it mean? Oh, so like the x value when it's
Yeah, so if I had my roots and I had x equals 4, that's a positive root.
What if it was 6?
If we had 6 sign changes,
So would it just be 0?
it'd be 6 or 4 or 2 or 0. You have to keep subtracting 2. Yeah, it's fun.
You have to put 4 in the middle of each one.
Yes, I always do that way. You remember it's options, not guarantees. So now let's do our negative roots. For our negative roots, we plug negative x in for x and we simplify. So I have 2 times negative x to the 5th minus 7 times negative x to the 4th plus 3 times negative x squared plus 6 times a negative x minus 5. Some people get really confused when we start taking negative x to like the 4th and the 5th and the 6th exponents. So this is the same as taking 2 times negative 1 to the 5th times x to the 5th, because negative x is the same as negative 1 times x, minus 7 times negative 1 to the 4th times x to the 4th, plus 3 times negative 1 squared times x squared, plus 6 times negative 1 times x, and then minus 5. And then I simplify by taking -1 to each of those exponents. So what do I get when I take -1 and raise it to the 5th power? I get a negative. So then I'm going to have -1 times 2, which will become -2x to the 5th. What do I get when I take -1 to the 4th power? Positive, so it doesn't change the sign. Because +1 times a -7 is still a -7. Same thing happens when I take -1 and I square it. It becomes a positive. So I still have plus 3x squared.
I'm still on like the first line. I don't even know what's
I
going
can
on.
do the odd and even ones.
So if it's an odd exponent, it changes signs. If it's an even exponent, it stays the same. It's a rule. What are you confused on?
Why do you write it?
No, I just, like when it's saying to like find whether it's odd or even, and you're supposed to plug in the f of -x.
Mm-hmm.
I thought you just changed the sign for everything.
We're just going to continue on. So for anybody who's confused, I separated the -1 and the x, and I took them each to the power that was designated. -1 to the 5th is the same as -1 times -1 times -1 times -1 times -1, which comes out to be a negative, so it changes the sign that was originally here. So it from a +2 to a -2. -1 to the 4th becomes positive, so +1 times -7 is still -7. -1 squared is +1, so that times 3 stays +3. Then I have -1 times 6 makes it a -6. And then -5 at the end doesn't change. So now I've plugged in -x and I've simplified. I need to count the number of sign changes I have occur. I do not have a sign change between my first two terms because they're both negative. I do have a sign change between my second and my third because it goes from a negative to a positive. I also have a sign change between my third and my fourth because it goes from a positive to a negative. I do not have a sign change between my fourth and my fifth because they're both negative. So when I talk about the number of negative roots I could have, how many sign changes did I have occur? 2. But I can subtract 2 from that. And 2 minus 2 is 0. So I have 2 negative roots or I have 0 negative roots.
Interesting.
So we count the number of sign changes that occur for our respective root. And we subtract 2 as many times as is possible. If I had 10 sign changes, you best believe I need to subtract 2 5 times. So I would have 10 or 8 or 6 or 4 or 2 or 0 roots, positive roots, whatever it is. I will not give you one that extensive for the most part. Okay.
So it's in the
Or I could ask a question like, when I solve this at f of x, I have 10 sign changes. How many positive roots are possible?
10.
Or 8, or 6, or 4, or 2, or 0. I wouldn't expect you to finish solving it out.
Ask that one more time.
Okay. So now what we do is we need to fill in with the appropriate number of complex roots to give us the total number of roots I need in total. How do I know how many roots my polynomial is going to have? The degree of my polynomial. So here, Gunnar, you were in fact correct, because this is a degree 5 polynomial. So when I set this up, each of my columns is going to have to add to 5. You'll see what I mean by columns here in a second. Okay. So I'm going to come over here.
I ran a different example line.
Nope, still same example.
What in the world? This is taking like 10 pages.
Okay, so I like to build a table. It just makes it a lot easier for me. In that table, I have 3 types of roots. I have the positive roots, I have the negative roots, and I have the complex roots. I found how many positive roots I could potentially have, correct? I had 3 or I had 1. But I also had 2 options for my negative roots. So I'm going to have to repeat them twice. So I had 3 or I had 1. And I had 3 or I had 1. You'll see why I'm doing this in a second.
Wait, why are you writing like
You will see why I'm doing it in a second. So write the options for the positive twice. Because for my negative roots, I had the option of 2 or 0. For each of these options, I need to test all the options I also have for my negative. So I had 2 or 2, or I had 0 or 0. Because I had 2 options for my negatives, I have to test each of those on each of the options for my positive. Gunnar already told us we need 5 roots in total. So when I add straight down, all of these columns have to add up to 5. And I just fill in with the number of complex roots that make that true. So on my first column, if I have 3 positives and 2 negatives, how many complex roots could I have? 0, because I'm already at 5.
What? What is going on?
I'm adding and filling in the appropriate number of complex roots to make it equal 5. So for example, if I have 1 positive and 2 negative, I need 2 because I only have 3 to start with, and I have to make it equal 5.
But there's like 4 positive and 4 negative roots, you have like 16.
Yeah. I will not give you one like that because it's not worth the time it takes to put into it. Okay.
15-minute classes.
Gunnar, if I have 3 positives and 0 negatives, what number would I have to put in here to make this equal 5?
I get the table, I just don't know why we're doing it. What are we solving for?
We're solving for the total possibilities of the distributions of roots.
It's or 2, right?
It's or 2, right? Because that makes it equal 5, and then I could have or 4 as well. Because if I had 1 positive and no negatives, I would have to have 4 complex to make it equal 5. So this is called completing Descartes' rules of signs table, which just allows us to know the types of roots that are possible. This is more helpful when we get no sign changes occurring, which tells us we can exclude completely a type of root. So either we'll have no positive roots or we'll have no negative roots.
What is complex root even?
It has an I in it.
Oh, so it's still on the line. It's on like the 0 y 0 line, but it's on the line.
It's a theoretical root. So no, it doesn't actually exist on our y equals 0 line.
What if y is negative 0? It doesn't exist. Like that.
Never seen that in my life.
You would not be able to graph a complex root. We don't use complex roots when we're graphing, we use them when we're solving. There's a difference because it doesn't exist on our real coordinate plane.
Why do they need to exist if they don't exist?
Just because they don't exist two-dimensionally does not mean they don't exist at all.
Actually,
There's a big difference between understanding just because we can see it doesn't mean that we're limited to just what we can see. There are an infinite number of realms and dimensions that mathematics deals with. So you need to open your mind a little bit to the possibility just because we can't see it doesn't mean it doesn't exist. It's kind of fun. Okay, so that was Descartes' rule of signs. I would not ask you an extremely difficult polynomial for this. But you can expect I will ask you some sort of Descartes' rule question tomorrow on the quiz. Your quiz is open note, so as long as you have this, you should be fairly okay. So then our last theorem is called the first theorem for bounds or of bounds for real zeros of polynomials. You know me so well, Nicole. So well. Yes.
Can they be? There can be complex zeros, can there? Or
Yes.
no?
Absolutely. If there's a complex, though, I'm not expecting you to graph it. It just means that we had a turn occur somewhere that didn't exist in our coordinate plane. That's what it means. So you're fine. Okay. So this is going to be a lot to write, but when we do an example, it will make much more sense. This also is way more helpful than the Descartes rule. I'm just saying. You just have to learn them both. So this says, Suppose f of x is a polynomial with real coefficients and a positive leading coefficient. Also suppose that this polynomial f of x is divided synthetically. This is where synthetic division comes in. I guess you could do it with long division too, it just goes so much faster. By some factor x minus c. There are two parts then to what's to follow. First part is, if that c that I divided out is positive, so if it's greater than 0, and if all numbers in the third row of our synthetic division chart are the same sign, so if they're all positive or they're all negative, or if they're 0, that counts too, then the value c I divided out is the upper bound for the real zeros of f of x.
My computer's killing me this time.
I know, I'm sorry. We may have to I might have to fix the seating chart so maybe people can see a little bit better. So this says if I divided out 4 and I got no sign changes in that third row from synthetic division, that means there is no root larger than 4 that is a factor of my polynomial. So that means if I had a list of numbers that I was testing, I could take everything after 4 and I could just cross it out because it cannot be a 0. So that's what upper bound allows us to do. It allows us to eliminate values that are either above or below when it comes to my bounds.
What is a bound?
So it's just kind of like a cutoff. So like if I divided out 4, like I just said, and I got no sign changes in that third row
What's the third row?
of our synthetic division chart. So I have first row, second row, third row.
That was really confusing.
So if I have no sign changes in that third row, that means there are no zeros that are larger than the 4 I just divided out. So I can take everything bigger than 4 and just cross it out because they can't work.
So if they're all like positive or something?
If they're all positive or they're all negative, yes. Then that's an upper bound.
Is the upper bound.
Yes.
What's an upper bound?
Next part of this,
Oh my gosh.
if that c value I'm dividing out is negative, so if it's less than 0, and if the numbers in the third row alternate signs, then c is the lower bound, or we can say is a lower bound. For the real zeros of our polynomial. So we are going to do an example
Nice.
that will hopefully help.
I can't sharpen my pencil. Why?
Alternate. Do you mean just like it changes like at least once?
No, it changes every term. So it would go from positive to negative to positive to negative, or negative to positive. Like each term alternates. You never have 2 terms with the same sign next to each other. Yes.
What if there's a 0?
Zeros count as whatever sign I need it to be.
So it's all.
So it's a wild.
They're like a wild card. Yeah. Okay, so let's do an example because I know you guys are like super confused probably. So this one says to find the upper and the lower bounds for the real solutions of this polynomial, 2x cubed plus 5x squared minus 8x minus 7. And I've told you where to start. Okay, so we're not to the point yet where you are making your own list of values to test. We're at the point where I'm telling you what we're kind of working with and you have to figure it out from there. I did give you a question in your homework where I gave you values to work from as a note on that homework assignment. Hopefully you guys saw that, because if not, it could take you a hot minute. You'll see it's the last question on the homework. Look on the assignment. I put like a hint in there to help you.
I
Okay.
looked at it, but I didn't need to do it.
Okay. Well, you probably will do it now. Okay. So I'm gonna start by setting up my synthetic division chart. I love synthetic division. This makes me so happy.
Yeah,
Okay.
we love it.
So when I'm doing synthetic division, what's the first thing I need to check for?
Facts.
Did I skip any terms?
Yeah.
So I have a 3, I have a 2, I have a 1, and I have a 0. So I'm good to go. I did not skip any terms, so I don't have to fill in any zeros. So I set up my chart, and what I do, I have 2, 5, -8, -7. I build my chart. How do I decide what number I'm dividing out?
Whatever.
Okay, so I've given you 2 options. We just have to set them equal to 0 and solve for x. So we're going to start with x minus 1. So I take x minus 1, I set it equal to 0, and I solve for x, which gives me x equals 1. This is the number that I'm going to put in this top left corner, and I'm going to divide out using synthetic division.
Where we divide.
That's what division means.
So we're-
Well, we multiply to divide. It's kind of confusing, but so when I'm doing synthetic division, we always drop down our first coefficient first, all the way down to that 3rd row. Then I take that coefficient times the number I'm dividing out, and it goes under the next coefficient. So 2 times 1 is 2. Then I add straight down. 5 plus 2 is 7. Then I do 7 times 1 to get 7. -8 plus 7 is -1. -1 times 1 is -1. -7 plus a -1 is -8. So I'm trying to identify my upper and my lower bounds. Since I divided by a positive, this could only be an upper bound if I had no sign changes occurring in that 3rd row. Did I have any sign changes in that 3rd row?
Yeah.
Yes. So this is not an upper bound. So now I have to test the next one that it gave me.
It's giving me crazy Christmas vibes.
I know. Well, the red and the green show up really nice on the camera. So I'm trying to use colors that show up really nice, but I think I might switch to blue. Other blue. Okay, so x minus 1 didn't work since I didn't have the same sign in all of my terms. So now I'm going to try the x minus 2. Same thing as before. I'm going to take the x minus 2 and I'm going to set it equal to 0 and solve for x. And when I do, I get x equals 2. So 2 is the number that's going to go in that top left box. And then I do it all over again. This first coefficient is always the one that drops straight down. So then I take 2 times 2 and I get 4, which goes under my next coefficient. Add straight down, 5 plus 4 is 9. Then I get 9 times 2 is 18. -8 plus 18 is 10. 10 times 2 is 20, which gives me a positive 13 when I take -7 plus 20. Positive 13. Did I have any sign changes?
No.
Did I divide by a positive number?
Yeah.
So this is an upper bound to this polynomial, which means if I were finding any real roots, none of my roots would be larger than 2. That's what upper bound means. It means this is the highest limit that any of my roots could potentially be. Nothing beyond that could be a root. Okay, so x minus 2 is an upper bound, which you could also say x equals 2.
what if like 1.5 was, but we didn't test 1.5?
Well, we're not trying to find the zeros right now. We're trying to find the bounds. So there will come a point where you have to test things like fractions,
But what if it was that? You didn't know.
which is why this is an upper bound, not necessarily the upper bound. Because sometimes you could think that this is an upper bound and you test a number lower than it. It turns out that's an upper bound as well. That's completely okay. All it's helping you do is eliminate possible values, which makes your life a little bit easier. So now let's go ahead and do the lower bound. So for lower bound, I'm going to try dividing out x plus 3 and x plus 4 using that same setup, so my coefficients are not changing.
We're doing another one?
We're doing lower bound. We only did upper bound before
How was that now? Or how was that now?
because I didn't divide out a negative number.
Oh. I see.
Lower bound only
I
applies
see
when
what
we're
you're saying
dividing out
now.
a negative. Upper bound only applies when we're dividing out a positive, so make sure you're keeping track of that. I set up my synthetic division chart. Now I just have to have a number to divide out. So we're going to use x plus 3 because it's the first one that was listed. I set that equal to 0. I solve for x, and I get x equals negative 3. This is, in fact, a negative number. So that means if I'm looking for a bound, it's going to be a lower bound. So I'm looking for alternating terms, so alternating signs in that third row. If I don't have alternating signs, it is not a lower bound. So let's do it. The 2 drops straight down. 2 times a negative 3 becomes negative 6. 5 plus negative 6 is negative 1. So far, so good. I have a positive and a negative. Let's see how it goes. Negative 1 times a negative 3 is a positive 3. Negative 8 plus 3 is a negative 5. I could stop right here because these are not alternating. I have 2 negatives in a row, which tells me that negative 3 is not a bound. Or we could just cross it out. And then I move on to the next value that I'm trying. So here, I'm going to do x plus 4. I'm going to erase all this. Interesting, right? So much fun. X plus 4 is the next one I was told to test. I set that equal to 0 and I solve for x and I get negative 4. Again, this is a negative value, so if I'm looking for a bound, it will be a lower bound. The first coefficient drops all the way down just like normal. Then 2 times a negative 4 gives me a negative 8. 5 plus a negative 8 is a negative 3. So far, so good. Negative 3 times a negative 4 is a positive 12. Negative 8 plus 12 is 4. Oh, we're still going really, really well here because it keeps changing. 4 times a negative 4 is a negative 16. Negative 7 and negative 16 give me a negative 23. So because each term changed signs, or I didn't have 2 terms next to each other with the same sign, then this is a lower bound, which means if I were testing for zeros, I could eliminate anything that's less than negative 4 because it could not possibly work. So x equals negative 4 is a lower bound for the polynomial f of x I started with. Which means that all of the zeros that I could get have to fall between this lower bound of negative 4 and the upper bound of positive 2. So that's another helpful thing to know. So all real zeros fall between x equals negative 4 and x equals 2, since those were my lower and upper bounds. And that's a lot easier to work with, because that's a finite number, than every single number that we could possibly think of. Because that's kind of where you start with sometimes when you're thinking about polynomials. And this is where we stop. So your homework is on Canvas. It should be the same one that you started to work on Friday. It is 7 questions. Do not forget you have the quiz tomorrow, which is open note. It is open note, so make sure you bring your notes with you. Only written notes are allowed. Okay? Don't look at me like that, Marissa.
I'm ready to go back to bed.
Huh?
The video lesson was happening up there.
I just mean you can't print my notes and bring them in.
So
That's kind of not okay.
I was about
I can write your notes.
Any questions, Zoe?
Yeah, I have a question.
What?